Hello and welcome. In this video, we are going to look at the analysis technique known as mesh current analysis. In this technique, we apply KVL, Kirchhoff's voltage law, to generate a set of equations that we will then solve to determine the mesh currents and then the other physical quantities, voltages and currents in the rest of the circuit. So let's begin. My acronym for mesh current analysis is MCA, and then I say MCA in conjunction with KVL is our analysis technique. Okay, so first thing that I would like to point out is that mesh currents are completely hypothetical. Okay, mesh currents are completely hypothetical. They are not real. They do not exist in real life. Okay, so hypothetical or theoretical, if you will. They are theoretical. Contrary to branch currents, which is the actual current that is flowing through a branch. So if you look at this image here on the left, we can see that there are three meshes. You have mesh 1, mesh 2, and mesh 3. Okay, let's label them as M1, M2, and M3. And each one of these has a hypothetical mesh current that is flowing inside the mesh. Okay, so you have I1 right here, I2 right there, and I3 right there, each respectively. Now, for simplicity's sake, we would always like to choose a common direction for the currents. And by common, I mean they should be either clockwise or anti-clockwise or counterclockwise. But that's not necessarily the case for each and every single problem. Here we can see that all of the mesh currents are clockwise, right? All of them are clockwise. They are going or they're flowing in that direction. Also, if you notice, each shared branch, meaning a shared branch R2 or R3 or this voltage source VB, it's known as a shared branch because that component is shared between two meshes. So R2 is shared between mesh 1 and 3, R3 is shared between 1 and 2, and voltage source VB is shared between 2 and 3. And so you can see the mesh currents are actually shared between between that component. That's right. That component has both I1 and I3 flowing through it, which in real life or in physical sense is not at all possible. Okay, it will only flow in one direction. So that's why we say that they are hypothetical, right? Completely theoretical, just for the purposes of analysis. Now, based on the mesh currents, we can write KVL equations around the loop, meaning we can write a KVL equation here, we can write a KVL equation here, we can write a KVL equation here. Because when current flows, it causes a voltage drop. And when you have a voltage drop, we can sum up those voltages. Law of conservation of energy applies, and we can sum them all up to 0. So the steps involved in mesh current analysis are something like this. We first identify all the meshes in the circuit. We choose and assign mesh currents with the direction. Now, my preferred method is always to choose clockwise, but you can choose clockwise or counterclockwise. It makes absolutely no difference in your solution. Okay, absolutely no difference in your solution. Choose either. Once you have that, you apply KVL to each mesh, right? Once you apply KVL to each mesh, you will have a set of voltages, right? Once you have a set of voltages, you apply Ohm's law to those voltages, and you express each voltage in terms of the mesh currents. Okay. And then once you have each voltage in terms of the mesh currents, you can reduce the equations in the form of AX plus or minus BY plus or minus CZ is equal to D, where X, Y, and Z are your unknown variables. Or your mesh currents. And once you solve for your mesh currents, you can then solve for any voltage or any current in the circuit. So let's see how it would work in the example circuit of the previous slide. Right. So we have here 3 meshes, 1 voltage source V8, second voltage source VB, and 3 mesh currents. And the point here would be, let's take resistor R1 as an example. If you take resistor R1 and we choose the mesh current I3 to flow in the clockwise direction, we know that VR3 would be plus on the left, minus on the right. Sorry, VR1. But then if we take a look at R2, R2 actually has 2 currents, right? I1 going in this direction. Actually, let's move R2 out here. And then I3 flowing in this direction. So if we follow the hypothetical assumptions of 2 currents flowing in there, they should cause 2 voltage drops, plus minus this way and plus minus this way. Now, when you add up the voltages, we have to pick a direction, right, to sum up the voltages. Typically, what I do is I also add up my voltages or apply KVL also in a clockwise direction. It doesn't actually matter how you add them up, whether you add them up clockwise or counterclockwise, does not really matter. But let's say I add up my voltages in a clockwise direction. So I'm adding up the voltages going from left to right. So I would have VR2 as equal to R1 times I1 minus I3. Because again, remember, it's 2 mesh currents causing 1 single branch current, right? The actual branch current that's flowing through R2 can be written as, let's say, VR2 is equal to whatever that current is, I times R2. This should be R2. But then IR2 is made up of the mesh currents I1 and I3, right? I1 and I3. And because the KVL direction chosen is clockwise, it'll be I1 minus I3. But here's the thing. When we apply KVL to mesh 1, so let's go ahead and apply KVL to mesh 1. If you apply KVL to mesh 1, we have 3 voltages. I have VA, I have VR2, and I have VR3. They should all sum up to 0, right? So VA would be minus, VR2 would be plus, VR3 would be plus. And thus I have my KVL equation, right? Now VA, of course, would be known to us. But if I'm summing up the voltages in mesh 1, that means that my VR2 is going to be plus R2 to I1 minus I3. And then R3 is going to be R3 times I1 minus I2 is equal to 0. Think over it for a few seconds. Because when we get to M2 and we apply the same KVL in the clockwise direction, I would have 3 voltages again. I would have VR3, I have VB, and I have VR4 equal to 0. This time all of my voltages are positive. So all my voltages are positive. VR3 can be written as, now here's the critical difference, because I2 is flowing in the same direction as my KVL direction, it would become I2 minus I1. In the first instance, in mesh 1, I1 was flowing in the same direction as my KVL direction. Here I2 is in the same direction, and so in mesh 1 it is I1 minus I2, and in mesh 2 it's I2 minus I1, and then plus VB plus VR4, and VR4 of course is not a shared branch, so I can simply write it as I2 times R4 equal to 0. Hope that makes sense. And let's go ahead and finish up mesh 3. So if I write out mesh 3 is going to be, again, 3 voltages, R1, R2, and VB. I'm going to start from the bottom left corner again. So I would have VR2, VR1, and I have VB equal to 0. In this case, I'm going to have, again, positive for all, right? Positive for all. VR2 is now going to have KVL and I3 flowing in the same direction. And so VR2 is going to be R2 into I3 minus I1 plus VR1, which is not shared, right? So it's simply I3 times R1 plus VB is equal to 0. Oh, VB is actually minus, sorry. VB is actually minus, right? If I'm applying KVL in the clockwise direction, I encounter the minus sign first, so VB would be minus. So thus I have VR2 plus VR1 minus VB is equal to 0. VR2, if you notice here, is I1 minus I3, again, because of KVL directions. And here it is I3 minus I1, again, because of KVL direction, matching up with the same mesh current direction. So once you have these, you simply plug in all the known values, you reduce the equations to the form of AX plus or minus BY is equal to C, where X, Y are your variables or your unknown mesh currents. And then once you have your mesh currents, you plug and solve. You can find any voltage and any current in any part of the circuit. And that, in short, is mesh current analysis.